All right, we continue our afternoon session with a talk by Hülya Argüz, and she's going to tell us about quivers and Pierrick dimensions. Hülya?
Thank you very much. Many thanks to the organizers for providing me the opportunity to speak at this very nice conference. So the plan of my talk is as follows. I will essentially tell you how to bridge two topics, one in algebra and one in geometry. On the algebra side, I will tell you about quiver DT invariants, quiver Donaldson-Thomas invariants, and I will explain how to calculate these invariants using the attractive law tree formula, which was something we did in 2020 with Pierrick. And on the geometry side, I will tell you about counts of log curves and toric varieties, and tell you how to construct toric varieties from quivers, and how to enumerate log curves. And the main result will be a relationship between quiver DT invariants and log Gromov Witten invariants of toric varieties. And at the very end, I will also tell a relationship, a correspondence between quiver DT invariants and log Gromov Witten invariants of cluster varieties. So this first part relationship between toric varieties will be on archive next week, and the second part with cluster varieties will come out soon. Okay, so I will have a smooth start with quivers. Just to recall the terminology, a quiver is a finite-oriented graph Q with a set of vertices Q0 and set of arrows Q1. There is a map S mapping an arrow to its source, and T mapping an arrow to its target. And we consider a representation of a quiver, which is assignment of a vector space to every vertex of the quiver, and a linear transformation for every arrow between the two corresponding vertices. And we will fix throughout the talk a dimension vector when we talk about quiver representations, which is an element gamma of the lattice n, plus where n is the lattice z to the number of vertices of the quiver. And like in this example, if you have a quiver just with 3 vertices, the dimension vector records the dimensions of the vector spaces 1, 2, and 1 that you assign to the vertices. There is a natural notion of morphisms, isomorphisms between quiver representations, and we will consider the moduli space of quiver representations up to isomorphisms. And we will also fix a stability parameter. So here there's a notion of kink stability whenever you have a quiver representation of dimension gamma. You fix an element theta in gamma perp. It's called a stability parameter, and if for any sub-representation of theta of dimension b prime, the sub-representation is smaller than 0, then you call your representation stable. If it's smaller or equal to 0, it's called semi-stable. And I will denote by m gamma theta the moduli space of theta semi-stable quiver representations of dimension gamma. In nice cases, in situations when this moduli space is smooth, we will define quiver DT invariants just as the topological early characteristics of this moduli space. And the most significant property when we talk about quiver DT invariants is that there is a piecewise constant dependence on the stability parameter theta, which means there's a wall and chamber structure in gamma perp. So if you vary your stability parameter theta, as long as you're inside one of the green chambers, in this example, your quiver DT invariants will remain constant, invariant, and if you cross some wall, they will change by some wall crossing. Just as a simple example, if you look at the M-Kronecker quiver, which is the quiver with 2 vertices and n arrows between them, and assume I fix my dimension vector 1, 1, So you can imagine a linear map from C to C is determined by some complex number, and this king stability imposes that we should not have all of the complex numbers to be 0. So in this case, your moduli space, if non-empty, is going to be isomorphic to the complex projective space of dimension n-1. There's a typo here, sorry, this is n-1 for the n-chronic equivalent. And generally, we do consider quivers with some potential. So this was the n-chronic quiver was a very simple case where we didn't have cycles, but we consider generally the path algebra, whose elements are given by linear combinations of paths in Q, and a potential is a formal linear combination of oriented cycles. So we will consider quivers with potential. In this situation, to define the dt invariance, we will consider a trace function. So for any cycle C, you look at the compositions of all the linear maps that are assigned to the arrows forming C, and you define your trace function as the sum of the traces of these linear maps. And in situations when your critical locus is again nice, which means your moduli space is smooth, and so on, here you can define your quiver dt invariance for quivers with potentials as the Euler characteristic of the critical locus. And generally, here is the general definition. Generally, you will not be in so nice situations, so you need to consider the sheaf cohomology groups, and you sum up, you consider an alternating sum of ranks of sheaf cohomology groups. And the sheaf you consider here is, I will just tell you in this slide, I will not tell in detail. It's called intersection cohomology sheaf. This is a perverse sheaf. In situations when your moduli space is smooth, it's a constant sheaf with tau Q on your moduli space and gamma theta. And then you apply some factor called the vanishing cycle factor to this sheaf to obtain a sheaf on the critical locus. And then you define your dt invariance as the Euler characteristic of the critical locus with this sheaf cohomology groups. And we will generally not work with these dt invariants just for computational convenience. We will consider what people call rational dt invariants. If you know the set of data of all rational dt invariants, it's equivalent to the set of data of dt invariants. It's just for computational convenience, like due to factors appearing in wall crossing, essentially, we will consider -1 to the k -1 over k square of gamma omega theta. And there is a lot of literature, so I just wrote here some names if you want to look up these. This theory is due to Kontsevich, Seubelman, Joyce, Song, Kranika, Davison, Meinhardt, and so on. As there are some physicists in the audience, I will just spell some words, though it's beyond my expertise. I'm not really a physicist. So there's natural work of, there's a literature, quivers naturally appear in n equal 2 for the SU3 super-Young-Mills theory. I took this table from the paper wall crossing and BPS joints, where all these numbers are calculated by physicists, and they do represent some quiver dt invariance. So as you can see, these numbers can be arbitrarily complicated. However, mathematicians also do have some motivation to understand quiver dt invariance, particularly because they're related to geometric Donaldson-Thomas theory, which is concerned with counting coherent sheaves in Calabi-Yau triples. And as we saw, homological mirror symmetry that everyone in this audience knows relates these counts of coherent sheaves to special Lagrangians. And furthermore, they're interesting for physicists because they appear in the context of supersymmetric quantum mechanics, and they have to do with supersymmetric counts of supersymmetric ground states or BPS particles. So a question that I was asking together with Pierrick is, while these numbers are complicated to compute, is there a way to calculate them out of the data of a simple primitive set of DT invariants? Is there such a primitive set from which we could determine all DT invariants? And there is a non-trivial intersection of this audience from the last talk I gave a couple of months ago at a meeting of this collaboration, where I was telling about some important counts of curves that are important for mirror symmetry and how to calculate them using an algorithmic wall crossing procedure out of simple curves. So I was telling, if you want to understand counts of like rational curves, you can just input the data of exceptional curves into a wall crossing algorithm, and this algorithm will tell you all such counts. So we generalized, we worked with some wall structures with some different Lie algebras than the talk I gave last time. And in this situation, we showed that you can also obtain an algorithm to combinatorially calculate quiver DT invariants out of some simpler DT invariants, and these DT invariants are called attractor DT invariants. So I will tell you what these DT invariants are in a minute. So to define them, I fixed a basis for n is the lattice Z to n, where n is the number of vertices of a quiver, and I define a skew-symmetric form on n by this formula where Aij. So the SISJ is defined as Aij minus Aj, where Aij is the number of arrows from I to j in your quiver. And for a fixed dimension vector in n, we call the point gamma slash in MR, the chamber containing this point, the attractor chamber. And we are defining attractor DT invariants as DT invariants where you choose your stability parameter from this attractor chamber. The definition is due to, it appears in works of Alexandru Piolin, Mozgova Piolin, and Kontsevich Soibelman. And they show that these attractor DT invariants, denoted by omega gamma star, do not depend on the stability parameter, and they're generally much simpler to calculate. So there is a theorem of Bridgeland, which proves that, for instance, if you have an acyclic quiver, then your attractor DT invariants for this quiver will be either 1 or 0. They will be equal to 1 if your dimension vector is one of the basis vectors of n, and 0 otherwise. And there is a conjecture of Hülya Argüz Piolin and Mozgova-Piolin. And they consider the situation if you have a local Del-Pezzo, Ks, by which we mean the canonical bundle over the Pezzo surface. If you look at a quiver with the additional data of a potential function, then there's a procedure to hook up. So there's a procedure to consider. So you can obtain a quiver QW such that the right bounded category of the representations of this quiver with potential will be isomorphic to the derived bounded category of coherent sheaves on your local Del-Pezzo. And then your attractor DT invariance will be 0 unless gamma is a multiple, gamma represents the multiple of a class of a point. And here I'm identifying the space n with the cohomology of the Del-Pezzo, local Del-Pezzo. And if it is the class of a multiple of a point, the DT invariants are going to be equal to the Euler characteristic of S. And there's a small typo here. They will also be non-zero, again, as in the first situation. If gamma is a basis vector, they will again be 1. So this conjecture was proven by Pierrick, Decomp, Leflouch, and Piolin for the situation when S is P2 in their recent work.
Sorry, I don't think I understand the significance of these attractor chambers. Why are they? Why does it? Why does this definition work?
Why does this attractor chamber definition work?
Like, why are these attractor chambers significant?
There are particular chambers where for stability parameters in these chambers, it is shown that you can explicitly calculate your quiver DT invariance for this. So like if you choose your stability parameter gamma slash by this particular attractor point, you can concretely calculate in some good cases. And generally this gamma slash can be not in the interior of a chamber, then you need to do some small perturbation to understand them, but this perturbation will not change the result. So they're just simpler to compute because it is known that if you look at any other chamber, you can start from the attractor chamber and you need to follow some wall crossing to arrive at another chamber. So like this attractor chamber is like the initial place where you can do some concrete calculations for this fixed parameter, stability parameter, given by this particular point in MR, given using this inner product.
Okay. Sure.
But you still need to know where all the balls are to implement what you want to go to.
That's correct. That's correct. Yes. So generally, there are like the typical situations, you can do some concrete calculations for this chamber, but if once you start crossing walls, there can be infinitely many walls and this can get arbitrarily complicated. So you still need to now keep track of the combinatorics and wall crossing. If you change your stability parameter away from the attractor chamber, so you need to keep track of the wall crossing, and that will tell you how we calculate those invariants once passing away from this attractor chamber. So the way I like to think of them is like when I did my work with Mark Ross that I talked about last time, I was talking about the bond structure and I was telling there's some nice Gromov Witten invariants which we immediately know how to calculate given by curves, exceptional curves. And so I like to think of these analogous to that situation, and we obtain all kinds of other Gromov Witten invariants once we input the data with lots of exceptional curves. Just because the procedure, the wall crossing algorithm works is sort of analogous. Sorry, was there any other question?
Yeah, so I was wondering, does this attractor mean the same thing? What physicists say black hole attractor?
Yeah, so this attractor, I think it does appear in papers a lot. I also saw these attractor clause in papers of Quivers, but I do believe it is dating back in the physics literature. Is that correct?
Yeah, the definitive terminology come from there, and he said some kind of simplified setup. Oh yeah,
Right.
Thanks.
Good. So in the paper of Quivers, they do describe attractor flaws dating back to 2013, and they show that if you have a quiver with potential, if you fix gamma a dimension vector, then there's an iterative application of what we call Quivers-Solverman wall crossing formula, which says that you can calculate general DT invariants in terms of attractor DT invariants. So on the right-hand side, there are attractor DT invariants, and there is some coefficients which you can explicitly calculate out of the wall crossing algorithm. And here, automorphism gamma I is the order of permutation symmetries you need to divide, as usual with that automorphisms, and they explain the coefficients appearing in this formula relating general DT invariants to attractor DT invariants can be combinatorially captured by looking at sums of trees with leaves decorated by this gamma 1 to gamma r. So, which is the decomposition of your dimension vector gamma. So we write gamma as decomposed as gamma 1 plus gamma r. And roughly the picture is as follows. So you have gamma perp, you start with a tree which stops at a point theta. When you look at Quivers dt invariance with stability parameter theta, you go in the direction of your attractor flow, so which is the direction of you input gamma in your skew symmetric form, and then you follow again once you decompose gamma into gamma i's, you follow this attractor flow. So in this story, what is challenging is to the fact that in the paper of Conseil-Soberman, like in this picture here, you can have arbitrary trees with arbitrary valencies, although they are like tropical trees, by which I mean they satisfy some tropical balancing condition, which means around every vertex, you can look at some weighted direction vectors and you impose them to be zero. There are some. Still, what we wanted to do is to obtain simpler trees, which are all trivalent, and make contact with tropical geometry, computationally effective tools of tropical geometry, if we reduce the situation to the trivalent case. So the idea is, in our work with Pierrick, is to perturb such diagrams. So we ended up with a formula, which is the flow tree formula conjectured by some physicists, saying that you can calculate general dt invariance in terms of attractor dt invariance, and you can obtain this coefficients fr theta gamma 1 to gamma r. You can concretely describe them in terms of binary trees. So I draw here a binary tree. These are simple trees where if you start at your point theta and r, if you orient them away from this point theta, so each time you cross a vertex, you divide into two directions. So they're trivalent trees. And this formula was conjectured that you can find this relationship between general dt invariance and attractor dt invariance by some physicists. And it's a conjecture, it was a conjecture of Alexandro Pioli. And we used in our work wall crossing, and we proved a more general attractive flow tree formula for wall structures and obtained this as a consequence. And I should say that a nice alternative proof of Moscow, which came out around the same time, is using operas. And it's an interesting question how these two different avenues might relate to each other, which we don't really know. So I will tell you a little bit about the coefficients fr theta. If you fix a quiver with potential and I fix my dimension vector gamma, I write it, I decompose it as a sum of gamma 1 to gamma r. And generally repetitions are allowed. For this slide only, I will have a simplifying assumption that I assume gamma 1 to gamma r is the basis. So we do write these coefficients fr gamma 1 to gamma r as a combinatorial sum over rooted binary trees tr. And inside the sum, there is the product over all vertices, interior vertices of tr. There is a sign epsilon. I used minus epsilon here as just for convention, because in our paper, we actually work with refined dt invariance where we have additional y and t parameters. For the purposes of the talk, to make everything compatible, I'm considering the limit as y goes to -1. And there's some, so we evaluate the skew symmetric form at EV prime, EV double prime. So which, like in this picture, if you have a vertex V, EV prime, EV double prime, are the children, I denote the dimension vectors corresponding to the descendants of V. So each time you have a vertex, if you follow the flow, there are two vertices descendant to V, which I denote which we denote by EV prime, EV double prime. And the technical story is in this paper from 2 years ago was to show you can actually have well-defined signs, and we describe these signs with some flaws, and we showed they have to do with the realizability of tropical trees. So in the general case, so here I had the simplifying assumption while telling the formula for FR thetas. In the general situation, these gamma 1 to gamma r does not need to be a basis. And we showed we can still work in a bigger space, which I denote by curly and enlarge the space, and define a map from curly n, and to find a new symmetric form, new skew-symmetric form, so that I can still do the perturbation of a higher valent attractive flow to a trivalent one. So as I mentioned, one of the purposes was when we have a attractive flow tree, like in the work of Konstovic-Soibelman, showing that we can make appropriate perturbations so that we can sum over binary trees. There is some technical issues to do that if some gamma i's to the composition of gamma into gamma 1 to gamma r. If gamma 1 to gamma r doesn't form a basis, then we need to work in bigger spaces, but still we can handle these situations and get our attractive flow tree formula. Just as an example, if we consider the n-chronic quiver that I mentioned at the beginning, a quiver with two vertices and n arrows between them, the dimension vector 1, 1, so your stability parameter theta and gamma perp can be any theta 1 minus theta 1. And if you consider the decomposition of gamma into 1, 0 and 0, 1, so this coefficient at 1 theta is just 1 because there's only one possible tree, and f2 theta is some sign times we calculate the inner product. So in this formula, this inner product EV prime prime was the number of arrows, and we can calculate it to be n. So in this case, you can calculate your DT invariants for the sub theta. You can show they equal to n if you do the calculation. So this was essentially all I wanted to tell you about DT, the story about quiver DT invariants. And as I advertised at the beginning of my talk, the goal of my talk was to tell you how to relate the story of quiver DT invariants to geometry of Kerr counts. So the goal is, in the remaining part, is to show you a correspondence, a relationship between FR theta gamma 1 to gamma r and counts of rational curves in a toric variety. I will tell you what this toric variety is and what kind of rational curves we're counting. So we define a toric variety out of the data of a quiver Q and gamma, an element of the lattice as follows. So we define a toric fan of a smooth projective toric variety containing all the rays are greater or equal to 0 times this vector where you take the skew-symmetric form and input gamma I, so this vector in MR. And generally, if you just consider these rays, you might not end up with a fan which is nice, which corresponds to a smooth projective toric variety. But you can always refine, add more rays, and it will not change the result. So you can take some subdivisions and obtain a fan containing all these rays. And this gives a toric variety. And to define the enumerative problem, we also define hypersurfaces from the data of the quiver or the dimension vector HI, and the toric boundary divisor DI, which is the divisor in the toric variety corresponding to this ray are greater than or equal 0, gamma I. And we define the hypersurface by the equation z to the gamma I is equal to some constant. And then the kind of curves we are looking at are genus 0 stable maps from C P1 to PR+1, where C is a nodal rational curve and P1 to PR+1 are marked points on this curve, to the toric variety sigma, And in our enumerative problem, we impose each marked point Pi to map onto the hypersurface in the toric boundary. In this case, when you have a surface, as I illustrated in the figure, your hypersurfaces inside the boundary will just be points. And we impose this condition for all but the last marked point, and we fix the contact orders of the images of these PIs as the divisibility of your vector gamma I. And now, as I told you, the kind of curves we are going to count, to be able to count these curves, finally, we arrived at safe waters of log geometry. This is what I love doing. So I did many years ago by now introduce log corals and tropical corals, and in my PhD, and only recently I came to realize some sharks related to virtual stuff in the story. So I will tell you a little bit about these. Okay, so this is a brief picture of what log Gromov Witten theory is about. So it's for counting curves with relative tangency conditions given relative to the divisor in a space. And in the situations when your divisor is smooth, this theory is due to Univ. It's called relative Gromov Witten theory. And he shows that to be able to do some curve counting, you need to construct some moduli spaces with nice properties. They need to be virtually smooth to extract numbers. And if you look at curves tangent to D, in the limit, they might fall out inside D. If you compactify your moduli spaces by this naive way with curves falling out, it won't be nice. So he has some construction of relative Gromov Witten invariants by using some compactifications using curves that live inside some bubbles. So he creates some accordion picture, modifies the target a little bit to be able to tell how to construct nice moduli spaces. This theory of Univ about relative Gromov Witten invariants was generalized by Gross-Ebert and Abramovich-Shen to the situation when you can consider not only smooth divisors D, but more general divisors, for instance, with normal crossing singularities. And a more generality would be called log smooth. In this situation, they develop a theory to construct moduli spaces by keeping track of the data of relative tangency conditions using some sheaves. And I will tell you what these sheaves are. They're called log structures. And the significant differences in this theory, we do not modify the target. We just make use of the data of sheaves to keep track of our enumerative problem, in particular of contact orders and so on. So here is the definition of a log structure. On a space, it could be a complex algebraic space or a scheme. X, you have a sheaf of monads Mx, and the log structure is given by the data of a map from M. This should be Mx, sorry, to your structure sheaf, and you impose this map to restrict to an isomorphism on the invertible elements of the structure sheaf. And log scheme is a scheme with a log structure. And I will in a minute give an example of a log structure. There is this discrete data of a log structure always when you get rid of the copy of the isomorphic elements of your when you get rid of the isomorphic copy of the invertible elements of your structure sheaf, you obtain a sheaf which we denote by M bar, which is called the Gauss sheaf, and we do most of the combinatorics we need using this Gauss sheaf. For instance, we define the tropicalization of a log scheme by using this data of this Gauss force. And the tropicalization of a log scheme is a cone complex given by the union of cones given by Hom from M bars, the Gauss sheaf, to R greater or equal to 0, modulo some identifications which are given by generalization and specialization maps. Here's an example. If you look at a space X, if you consider a divisor in X, and so I denote by the complement of this divisor X minus D to X by J, then you can describe a log structure called the divisory log structure by looking at the sheaf of regular functions of x on x, and you take all those regular functions which are invertible away from B. And so in this case, your morphism from this monoid to your structure sheaf is just the inclusion. And this defines, for instance, if you have A1, usual affine line with parameter T, this description of saying that the stalk around origin, if you take origin as your divisor, is given by all functions of the form h times Tn, because these are the ones invertible. And if you get rid of the h, it means passing through the Gauss sheaf, you can identify the T to n's with n's in natural numbers. So the Gauss sheaf will be isomorphic to n in this case. And the tropicalization will in this situation will be from n to r greater or equal 0, so it will just be r greater or equal 0, which is the same thing as the toric fun of A1. And if you consider a toric variety generally, then take B to be the toric boundary divisor, the tropicalization will be the toric fun. If you look at once you have log structures on a scheme, you can pull them back. Like you can pull the log structure on A1 back to this origin, and you will obtain log structure on a point. So it's called the standard log point. If you consider this log structure, pull it back, this you obtain on spec C. You will obtain monoids, sheaf of monoids, C star direct sum n of rank n. And generally, we will consider, for instance, the standard log point if you work with one parameter degenerations. We will consider like schemes over the standard log point, and in the situation when we work with families of curves in these schemes. So I will tell you in a minute about this. So first I want to define what a stable log map is. I fix a log point and log scheme over this log point, and SMS, which I denote by this log point, depending on the context, could be either a trivial log point, which means M is just C star, or the standard log point, like here, that I define C star direct sum n. It will be the trivial log point if you're interested in counting curves only in a fixed target X. It will be the standard log point if you're looking at degenerations, for instance, if you want to count log curves in the central fiber of a one parameter degeneration, and so on. And the stable log map with target X over S, by definition, is a commutative diagram from your domain curve CMC. There's a natural log structure on this domain curve. If you impose this domain curve to be what we call there's some technical condition to be log smooth over the standard or over some log point. And this local structure on this domain curve, the log structure, is described nicely in the work of Kato, Fumiharu Kato. And it's a commutative diagram, so your domain is log smooth over any log point, and you want your target to be a scheme over some other log point. And if you look at this definition, if you just consider the moduli space of any stable log map without any assumption on W, where your domain curve is log smooth over, this is gonna define you a very difficult to handle moduli space. It will be too wild. So what we do is we look at log maps of a fixed combinatorial type, which will fix this W for us. So I will use the data of a combinatorial type to fix this scheme W. By definition, the combinatorial type of a stable log map is the data of the dual intersection graph of your curve, and the data of a map sigma, which tells you if you consider the tropicalizations, namely, if you consider the dual intersection graph where the vertices and edges and legs of the dual intersection graph of C map in the tropicalization of X. And finally, you fix the contact orders. So once you fix such a combinatorial type only out of this data, you can define a monoid, which we call basic monoids. It's easier to define this basic monoid by first defining its dual, the dual of this basic monoid is defined as follows. It's a submonoid inside the space where you, for each node of your domain curve, you get a copy of M. For each generic point theta, I'm looking at the monoid with my Gauss sheet, the slope of it at f of theta. And so I'm defining a submonoid where I allow to vary vertices V, eta, and EQ denotes the edges of the dual graph. And by this construction that I just put this monoid QT, which is the dual of this, it's just gonna keep track of the deformations of your tropical maps corresponding to your log maps, where you can tropicalize things using this tropicalization definition that I told a minute ago. And this monoid, which only depends on combinatorial type, is going to tell you what is the moduli space of tropical curves of fixed combinatorial type. So if you consider home of this monoid to r greater or equal 0, you obtain the moduli space, which is a cone because you can scale, of tropical curves. So it is the work of Abramovich-Chan and Gross-Seibert to describe concrete invariants out of such curves. To do this, they show that if you look at, so first they have this definition of a stable log map, which is basic. So given a stable log map, one can show that there's a canonical map from this monoid Q to M bar W, where Q is the basic monoid defined by the combinatorial type. And we call a log map basic if we fix this MW in the description of this stable log map to be Q. And in this case, Abramovich-Chan and Gross-Seibert prove that if you look at the moduli space of all basic stable log maps with target X over S, this is a Debye-Mumford stack. And in this situation, they can describe, they show nice properties of this moduli space, and they describe a virtual fundamental class, which could define you log Gromov Witten invariants. So to do that, they fix genus, G, homology class beta, and the data of a tuple of contact orders. And the theorem is if you have a schema of S which is proper, then the moduli space of all log maps to X of class beta of genus G satisfying contact orders U is a proper Debye-Mumford stack. And if it is log smooth, it admits the virtual fundamental class. And this virtual fundamental class defines you an invariant called a log Gromov Witten invariant. And it was the work of Nishinoue and Seibert to show how to calculate and enumerate log Gromov Witten invariants, which are counts given by in the genus 0 situation. So if you just look at counts of rational maps in n-dimensional toric varieties, so this is a very restricted setup. So the general theory of log Gromov Witten invariants work for any scheme. So if we just focus on toric varieties and rational maps, it is shown by Nishinoue and Seibert that you can obtain the log Gromov Witten invariants rather nicely. There's no scary virtual stuff going on here. You can just count them in terms of counts of tropical trees in Rn. And our work that I will tell in the last few minutes will be based on this idea, but unlike in Nishinoue and Seibert, we will not work with single tropical curves. We will need to consider families of tropical curves. So there will be a significant generalization if you want to obtain a correspondence between families of tropical curves and some log maps. So working with families of tropical curves will amount to working with log maps where I described all these basic monoids. The basic monoids, WMWs, are going to be given by monoids of some higher rank in the story that I will tell you. So I will have log maps or higher rank basic monoids that I will relate to quiver DT invariants. So here are families of tropical curves that we are considering. First, we construct a D-2-dimensional family of tropical curves from an attractor tree T, which starts at a point theta in gamma per. And so the red thing is red tropical curve is obtained by following the direction of the flow. And we can extend this point theta in a natural way so that it looks really like a tropical curve in the usual sense. And we consider the formations of these tropical curves in d-2 dimensional families, which do trace out all our chambers gamma perps. And our goal is to try to make sense, try to find a correspondence theorem with these families of tropical curves that appear naturally and counts of law curves. So we show first, if you fix the general constraints, HIs are given by hypersurfaces in the toric boundary. If you look at the moduli space of genus 0 log curves in the toric variety defined by the quiver that I mentioned, whose tropicalization is the d-2 dimensional family of tropical curves, then this moduli space is finite, and we denote by n toric the number of such log curves. And our theorem states that the coefficients fr theta expressing the contribution of in the attractive flow tree formula that I mentioned, when you relate general DT invariants to attractive DT invariants, they're determined with these coefficients. We prove that this fr theta is equal to the n toric, which is the count of log curves in the toric variety. I will tell you a summary of the proof. So to prove this, the first step is follow a slightly similar strategy as initial Z-bats. We first to consider a toric degeneration of our toric variety. And in this degeneration, we also consider a degeneration of these constraints. And we have a degeneration formula which allows us to express invariance of the toric variety in terms of the counts of log curves in the central fiber of such a degeneration. And we show that we can obtain counts of log curves in the central fiber as a product of vertices, all possible vertices. So of gamma v prime prime. So these were for any vertex, these were the descendants in my attractive flow tree story in the binary trees. And then there is some technical points of the theory of punctured log Gromov Witten invariance due to Abramovich and Gross-Debet. We show that this product which appeared in the attractive flow tree story while calculating the coefficients of our thetas also agrees with the number of ways you can glue together log maps in different components of the central fiber. So there is a gluing formula in this context, and in this gluing formula there appear some numbers of ways to glue together log maps, and the technical point is to show that this gluing number of ways of gluing can be given by this number which appears in the quiver DT story. And so we had shown in the work that I mentioned at the beginning that in the quiver DT story you have these coefficients which can be given by this number. So by showing we can relate both of them to this number defined by using the skew-symmetric form and the data of the quiver with a dimension vector, we obtain a relationship between this toric log counts, curves of log curves and toric varieties and quiver DT invariants. In the remaining 5-10 minutes, I want to tell you, so this paper with this result that we show how to relate, how to find a relationship relating quiver DT invariance to log Gromov Witten invariance of toric varieties. It will be on arXiv next week or so. We are doing the final proofreading, but we have been working on a similar problem, which will come out a little later. So we were thinking, could we find a correspondence theorem between quiver DT invariance and counts of log curves, not in toric varieties, but more general cluster varieties? And I will also tell you the statement in this situation. So Cluster varieties are like generalizations of toric varieties. They contain C star to N, the algebraic tori. They contain copies of them, and you obtain cluster varieties by gluing together copies of algebraic tori. To construct cluster varieties, you can describe them combinatorially in terms of mutations of your quiver, and they're using like cluster transformations, telling you how to glue algebraic tori. There is also a geometric way to construct them, explained in the paper of Grossack and Kiel, which says that if you have a quiver Q, then you can construct a toric fund, just as I described. If you take bases for your lattice n, z to the number of vertices in Q, I denote the spaces again by Si, and I define Vi to be this element in the dual lattice M given by defined by using the skew-symmetric pairing. And I consider a toric fan containing all these rays are greater or equal to 0 Vi. And I consider again the hypersurfaces 1 plus Z to Zi equals 0 this time inside the toric boundary component. And if you blow up all these hypersurfaces, then what you obtain is a cluster variety up to some codimension 2 locus. This is the result of Grossack and Kiel, and we never really care about this codimension 2 locus when we talk about like ring of regular functions and so on. So this way, by blowing up these hypersurfaces, we obtain cluster varieties. And in this setup, when you look at cluster varieties, the curves that are related to quiver dt invariants are A1 curves, which are rational curves in your cluster variety, meeting the divisor D, which is the strict transform of the toric boundary divisor when you blow up the hypersurfaces in the boundary. And the curves are A1 curves, so they are rational curves meeting D at a single point. And these curves come in D-2 dimensional families, so where D is the number of vertices. And we consider a compactification of the moduli space of all A1 curves of class beta. And it turns that this moduli space is of dimension D-2. To be able to extract invariants, what we do is we count 0-dimensional strata inside this moduli space. Such invariance appears in the work of Abramovich and Gross-Siebert, and in my work with Mark Gross from 2020 or 19, we provided an algorithm how to count such A1 curves. So just to recall, so on the algebra side, I had a quiver and quiver dt invariants. On the geometry side, I construct a cluster variety and look at the counts of A1 curves. And our theorem in our work in progress is stating that if you're in the situation where all your attracted dt invariants are trivial, then there's an explicit correspondence between your homological class beta and your dimension vector gamma, such that the sum of Gromov Witten invariance log curves of a given type theta, where you sum over all possible types, is equal to your quiver dt invariance. And this result is sort of compatible with the result I told you, the relationship between quiver dt invariance and log curves and toric varieties. Because whenever you have such a cluster variety obtained by blowing up your toric variety along hypersurfaces, you can degenerate this cluster variety into the toric variety that I considered in the previous part of my talk. And there is a relationship between counts of log curves in the cluster variety and counts of log curves in the toric variety, which is given by the degeneration formula. I will just share a final slide just to tell you the heuristic picture of the proof. If you consider the interior of your cluster variety, the complement of x, so x minus t, the complement of t and x, then this admits a Lagrangian torus vibration with base MR. And if you look at counts of A1 curves, So I try to draw some fibers of the source vibration, and your A1 such you see a single point will roughly look like this. They will have some contact borders with some singular fibers. If you look at the projection of such an A1 curve drawn in red into the space MR, the base space, which you view as the space of stability parameters for your Quiver DT invariants, then it is natural just heuristically to expect the counts of A1 curves have to do with calculating DT invariants, Quiver DT invariants. I will not say more about the proof. Thank you very much for your attention.
Maybe this is sort of related to the slide you just had about cluster varieties, but even in the toric case, kind of, how did you know to start studying these toric varieties? Like, why was it conjectured that the toric variety count would be the same as this DT count? Is it just because of this picture, like, oh, they both happen in the space MR?
No, that's a very good question, actually. So what we did observe, and one of the recent papers about compactifications cluster varieties, compactifications cluster varieties and cross-edit mirrors, is that there is a scattering diagram, the cluster scattering diagram, which one can use to construct cluster varieties, which is very closely related to the Richland scattering diagram, which is used by Richland to capture like Quiver DT variants, and we show that the scattering diagram is equivalent to a combinatorial constructed scattering diagram, which appears in my work with Mark Ross. So we had this observation, which appeared in our paper last summer, that there is this equivalence between two combinatorial scattering diagrams. One calculates Quiver DT invariants, the other calculates counts of A1 curves. So the proof of this is actually gonna just be based on the using the equivalence of two wall structures or scattering diagrams. And once you know this, it's natural to expect in Gromov Witten theory that the invariants of these cluster varieties obtained by blowups of toric varieties are related to the invariants of the toric variety. So we consider a similar generation of cluster varieties to toric varieties in our work with Mark while calculating the counts of A1 curves. So that's by some observation of relating two different wall structures. Maybe.
Yeah, maybe I can understand. So in general, for a toric variety, the corresponding curve is not going to be a genus one curve. Do your results only apply for like these canonical bundles of Lopano toric guys, or if I give you some arbitrary toric Calabi-Yau?
Yes.
Do you know how did you have a corresponding Quiver description of the GT theory?
Right.
Or only for the ones that are canonical bundle over quantum?
Not only for the ones that are canonical bundle over quantum, we only have a when you consider rational numbers. We take the boundary as we just look at genus zero curves. And I do believe one of the future goals is to see if we can obtain a Quiver description if we consider genus one or higher genus curves. That's a very interesting question. There's some work of Pierrick in the direction where you need to consider, like, I don't know if you want to say something about it.
Yeah, but we might keep developing about the Calabi-Yau, like the Calabi-Yau threefold. Like the dimension of the variety, like the dimension of density of Quivers. So it's maybe something there.
Right, and we just look at actually a very particular configuration of hyper surfaces that allow us to.
Yeah, I think it's like that in Quiver. There's a really deep like.
So this is the second part. If I give you a toric treatment, do you know how to count the DT invariants there? The one associated with like zero. So for a threefold, I get the curves and surface. So zero 1 and 2 compactifications. Do you know how to do the DP compactification in general or only for fun?
Yeah, I think I'll do that.
Only fun. So the corresponding curve would be a torus that is then actually but the mirror curve is well.
Yeah, but I don't think I'll do that.
But this isn't that how you get your trees and how you get your generating stuff? Isn't that of say this is how Quivers original. If I gave you say O-3 or 2 or like some other kind of thing, how do you grab the corresponding curve? So the corresponding mirror curve is a pi, and then you look at you can derive the quiver from this picture and you get this and graph.
Other questions? If not, let's thank Hülya again.